imagine you're in a spaceship.
Yeah.
And
Yeah.
you're going back in time, back to the early universe,
Okay.
like a few 100 million years after the Big Bang.
Wow.
And you come across um, this huge galaxy blazing with light from new stars forming.
Right.
But as you get closer to the center,
Yeah.
there's this incredible gravitational pull.
Mm-hmm.
It's like something you've never encountered before.
Yeah.
It's an engine black hole, a black hole billions of times the mass of our sun.
Uh-huh.
But here's the thing. Those black holes shouldn't even exist yet.
Right.
Welcome to Cosmos in a Pod, the Space and Astronomy series. Please like, comment, share, and subscribe.
Absolutely.
So the question is, how did these giant black holes form so early in the universe?
Yeah, that's a really great question, and it's a mystery that's been puzzling astronomers for decades.
Right.
The usual way we think black holes form is from a dying star collapsing in on itself. But
Right.
that takes a really long time. Billions of years. And the universe just wasn't old enough back then for stars to die and create black holes that big.
Okay, so we're saying that the standard model of how black holes form isn't wrong. It just
Yeah.
doesn't explain these supermassive ones.
Exactly. It works fine for the smaller black holes, but for these supermassive ones, especially the ones we see in the early universe, it just doesn't quite add up.
Yeah. So what are some of the other ideas about how they formed?
Well, one idea is something called primordial black holes.
Primordial black holes.
Yeah.
Those are the ones that formed right after the Big Bang.
Exactly. Imagine the conditions back then. So much energy and density, everything packed together.
Yeah.
Some scientists think that little pockets in all that chaos could have collapsed and formed black holes right away, no stars needed.
Wow, so like seeds of black holes scattered through the early universe.
Right, and that would give them a huge head start to grow into those supermassive ones.
But we haven't actually found any of these primordial black holes.
Not yet. It's a cool idea, but we need more evidence.
Okay, so we've got the standard model, which might be too slow, and the primordial black hole idea, which we haven't proven. What else is there?
Well, the most likely explanation right now is something called direct collapse.
Direct collapse.
Yeah, instead of a single star collapsing, you have a massive cloud of gas, millions of times the mass of the sun, collapsing directly into a black hole.
So they skip the whole star phase altogether.
Exactly, and this could explain how those supermassive black holes form so fast.
Okay, but even with direct collapse, wouldn't they still need to grow incredibly quickly?
That's the next part of the puzzle. We have to look at some extreme processes like super Eddington accretion and the role of galaxy mergers.
Okay, I'm hooked. Let's talk about that.
Great. So we know these black holes would have to grow super fast, even with that direct collapse start.
Yeah, how does that happen?
Well, it comes down to something called accretion.
I know that black holes suck in stuff, anything that gets too close.
Right. But it's not as simple as just falling straight in.
Okay.
All that gas and dust spirals inward around the black hole,
Hmm.
and it forms this swirling disks.
Oh yeah, I've seen pictures of those accretion disks.
And they get incredibly hot because of all the friction, and that releases a ton of energy.
So it's not just a silent, invisible process. They're blazing with energy.
Exactly. But there's a limit to how fast a black hole can grow this way.
Okay.
As it pulls in more matter, all that energy from the disk can actually start pushing away incoming gas.
So it's like a back pressure.
Exactly. And that limit on how fast it can grow is called the Eddington limit.
But you said these early black holes had to grow super fast. So how did they get around that limit?
Right. Well, some black holes might have gone through periods of super Eddington accretion.
Super Eddington accretion?
Yeah. Basically, they were breaking the speed limit.
Whoa, is there any proof of that?
Actually, yes. The James Webb Space Telescope saw a black hole growing 40 times faster than the Eddington limit.
40 times! That's insane. What could make them grow that fast?
One idea is that those powerful jets we see coming from black holes could be playing a role.
Those beams of energy.
Right. They blast out from the black hole's poles, and they might be diverting some of the energy away from the accretion disk.
So more material can fall in.
Yeah, it's a complex process, but the JWST is giving us a closer look.
Okay, so super Eddington accretion's part of it, but where does all that material even come from in the first place? It's not like there's an endless buffet out there.
That's a great question. And that leads us to galaxy mergers.
When galaxies crash into each other.
Exactly. And when that happens, the black holes at their centers get pulled together by gravity.
Oh, wow.
They start orbiting each other, getting closer and closer. It's a spectacular dance.
So it's not just a one-time meal. It's like a constant feast fueled by these mergers.
Exactly. And these mergers are amazing. They can trigger bursts of star formation, creating these beautiful cosmic fireworks.
It's mind-blowing to think about. But even black holes can't keep growing forever, right?
You're right. They do have a lifespan. They eventually run out of fuel as the universe expands and everything spreads out.
So what happens then? What's the final act?
It involves something called Hawking radiation.
Okay, I've heard of that, but I don't really get it.
It's based on quantum mechanics. You
Yeah.
see, even the empty space around a black hole is full of these things called virtual particles.
Virtual particles.
Yeah, it's like pairs of particles constantly popping in and out of existence. They borrow energy from the vacuum of space.
Okay.
And they usually destroy each other almost instantly. But near a black hole, something weird can happen.
What happens?
Sometimes one particle falls into the black hole and the other one escapes. And that escaping particle takes some of the black hole's energy with it.
So even though nothing can escape from inside the black hole, it's still losing energy.
Exactly. And over a really, really long time, this energy leak called Hawking radiation makes the black hole shrink.
And then what happens in the end? So we were talking about Hawking radiation and how black holes lose a tiny bit of energy over time.
Right.
But what happens when it's all gone, when there's no more black hole left?
Well, it's not exactly an explosion, but it's kind of like one.
Okay.
All that energy trapped inside has to go somewhere. So it releases this huge burst of energy and particles.
So the black hole disappears in a burst of energy.
Yeah, you could say that. It's more like an evaporation, though.
So no more black hole, just a little echo of radiation.
Right, and that radiation just spreads out into the universe.
It's kind of sad in a way. These giant black holes just fading away.
I guess so. But remember, this takes an incredibly long time, much longer than the current age of the universe.
Yeah, that's true.
And it brings us to this idea of the heat death of the universe.
Heat death. That sounds ominous.
It's just a theory, but it fits with what we know about physics.
Okay.
Imagine a universe where everything has run out of fuel. All the stars are dead, all the black holes have evaporated.
So just a cold, empty universe.
Pretty much, just a faint sea of particles spread out over unimaginable distances.
No more stars, no more galaxies, just darkness and silence.
It's the ultimate end state of the universe, according to thermodynamics.
Oh, wow. It's kind of amazing to think about.
It is. It makes you realize how precious our time in the universe is.
We're lucky to be here when things are still happening.
Exactly. We get to see stars being born, galaxies colliding, black holes growing. It's a pretty special time.
I agree. Well, this has been a fascinating deep dive into the world of supermassive black holes.
It has. And who knows what new discoveries await us in the future.
That's right. There's always more to learn.
Absolutely.
Thanks for joining us on Cosmos in a Pod.
It was my pleasure.
And to all our listeners, don't forget to subscribe to our YouTube channel for more explorations of the universe.
And keep looking up at the stars.
Until next time.